Okay, you're on now, so it's being recorded.
Okay, great. So yeah, for anybody who doesn't know me, I'm Cormac. I'm just going into fourth year electronic and computer engineering, and I got involved with this through Ola. I did telecommunications with Ola last year, so that's my story. So what we're going to look at today is Stokes vector direct detection. So these are the areas we're going to cover. So just a quick summary of the common methods of transmission that are used currently. We're going to look at what Stokes vectors are, and then how they're used for this method of transmission called Stokes vector direct detection. And then we're going to have a comparison of this method with some of the other common methods. So the current methods of transmission, so on the kind of more simplistic side or basic side, we've got intensity modulation with direct detection. I think everybody's fairly familiar with that. So as you know, it's one-dimensional, it's limited in transmission distance and data rate, but it's also relatively inexpensive and straightforward means. On the other kind of end of the scale, you have coherent detection systems. And these are basically, they all kind of revolve around the idea that you have on the receiving side some sort of local oscillator, which kind of provides, as I understand it, like a benchmark of phase, so that you can then compare what's coming in against this locally oscillated waveform, and therefore tell what the phase of the signal is that's coming in. So it means that you can use not only you can measure not only the intensity of the transmission, but also the phase of it, so you can fit in more information. And also it can, when you're dealing with fiber optics, it can be polarization multiplex, so you can send information on both the, say, the horizontal and the vertical, or the X and Y polarization orientations, if you like. So it can carry a lot more information over longer distances, but it's quite expensive, and the signal processing and the equipment required and so on is quite complex. So ideally, kind of what we're looking for is something in between that can overcome some of the disadvantages of the IMDD, but without being as complicated as the coherent detection systems. So Stokes vectors, so what are they, first of all? So they're basically a set of parameters that describe the state of polarization of light. And they can describe any state of polarization. So it doesn't matter whether the light doesn't have to be perfectly polarized in one orientation. It can be a combination of different polarizations, or it can be unpolarized. And one of the big advantages of this method is that you can measure the Stokes parameters, or the Stokes vector, purely by measuring the intensity of the light. So you don't need particularly complicated equipment. How they work then, so if we start off just kind of with a basic wave equation, if you like, so if we have, so just in one dimension, so if you have E, the electric field, that's basically described by, if we have the E hat as a unit vector, so we've got the amplitude multiplied by a complex exponential. So we've got K, which is the wave propagation constant, R, which is the position in space, omega, which is the frequency, and T, which is time. So using this equation, we can tell the value of the electric field vector at any point in space or in time. And then if we expand that then to 2 dimensions, we've essentially got the same thing, but in an X and a Y direction. And just to bear in mind, when we're looking at this, if we treat the EX and the EY, which are the amplitudes of the waves, if we treat those as scalars, then really it means that this 2D wave equation assumes that both polarization elements are perfectly in phase, which might not be the case when we're dealing with light. So we need, instead of treating those as scalars, we need to treat those as complex scalars. So we have them down here, we've EX equals AX by E to the J delta X, where delta X is the phase and AX is the amplitude. So we've got that for both directions. So we can tell, and we'll have a look in a minute how we do it kind of, but if we know the amplitude or the relative amplitudes and the phase of both the horizontal and vertical components, or the X and Y components, then we will know the exact state of polarization. Okay, so we're going to have a quick look at some of the different states of polarization that light can be in. So the first one, kind of the most straightforward one, is linearly polarized light. So we can see on the diagram that we've got, in blue, we've got a vertical component, and in red, we've got the horizontal component. Now, if those two components are perfectly in phase are out of phase by pi. So if they're, if you like, perfectly in phase or perfectly out of phase, then it means that the amplitude of both at any one point in time is going to remain constant relative to each other. So in other words, if we combine the two vectors, like the horizontal vector and the vertical vector, then the angle of the resulting vector is going to stay constant. So as long as we're perfectly in phase or out of phase, we're going to have perfectly linearly polarized light. The angle will depend on the relative amplitudes of the two. So, you know, if the horizontal amplitude dominates, then it's going to be a fairly horizontally orientated polarization, and vice versa. Circularly polarized then is kind of an interesting one. So this occurs where we have horizontal and vertical components are out of phase by plus or minus pi over 2. So we've got a phase difference of plus or minus pi over 2. And kind of what we find when we look at that is that, so the amplitude of the resulting vector then at any point along the waveform, we determine just using Pythagoras. So it's the square root of the sum of the squares of the amplitudes of the vertical and horizontal components. And if they're out of phase by pi over 2, then this formula here kind of describes it. So we've got sine of x squared plus sine of x plus pi over 2 squared, being the pi over 2 being the phase difference. And that term will always be constant. So no matter what point we are in the phase or along the wave, the amplitude will remain constant. And the orientation of the polarization will change according to the position along the wave that we are. So if we take, just for example, if we take the point where bear in mind we're out of phase by pi over 2 exactly. So if we take the point where the vertical component is at its maximum, then the horizontal component is going to be at 0, and then vice versa. And in between those 2 points, then they move smoothly. So what we find is actually almost like a linear polarization that's rotating constantly. And the direction of rotation will be determined by whether the phase difference is plus or minus pi over 2. So it'll either rotate clockwise or anti-clockwise. The third state then we have is elliptically polarized light. So this really occurs where the conditions for either linear or circular are not met. So in any other situation, pretty much we're going to have elliptical polarization. So those, we see the diagram here. So there's a couple of things that kind of govern the state of polarization. So we've got the angle of ellipticity, which is chi. That's going to vary between 0 and 45 degrees. So if it's 45 degrees, we've essentially got circular polarization. If it's 0, it means we've got linear polarization. So an elliptical polarization is obviously going to be somewhere between the two. And then of course we've got the angle of orientation, which is essentially the orientation of the main axis of the ellipse to the horizontal. So that's described in the diagram there by the angle psi. And then we've got the x and y, which are the amplitudes. Now, the interesting thing here is that both the angles chi and psi, so the angles of ellipticity and orientation, both of those can be described in terms of the amplitudes and phase of the horizontal and vertical components. So again, if we have the relative amplitudes and the phase difference between the horizontal and vertical components, then we're going to know the exact state of polarization, no matter what that is. Okay, so we'll move on then to Stokes vectors and how they work. So Stokes vector is essentially composed of 4 parameters. So we see them here. We've got S0, S1, S2, and S3. We'll have a look at what they actually are mathematically and then what they kind of signify each of them. So if we look at S0, it's the intensity of the X component plus the intensity of the Y component. So basically it's the total intensity of the light. Normally, Stokes vectors are stated in a normalized state, and they're normalized with reference to the value of S0. So in other words, whatever the intensity is, the overall light intensity, that's stated as 1, and everything else is stated relative to that. So if we look at S1 then, we've got the intensity of the X component minus the intensity of the Y component. So you can imagine then that obviously signifies the degree of horizontal polarization. So if the X component intensity dominates, then we know that the light is mostly horizontally polarized, or in fact if EY was 0, it would be perfectly horizontally polarized. S2 then is defined as twice the real part of EX by EY conjugate. And mathematically, that actually works out as if we treat EX and EY as simply an amplitude multiplied by a complex exponential, then mathematically 2 times the real part of the X EY conjugate works out as 2AXAY by the cosine of the phase difference between them, where AX and AY are the amplitudes. And what that actually signifies is the degree of 45-degree polarization. And that kind of makes sense when we look at it like this, that for 45-degree polarization, we know that that's linear polarization. So we know that the phase difference must be either 0 or pi for that to work. So cosine of a phase difference of 0 or pi works out at 1. So that cosine term is just reduced to 1. And then also for 45-degree polarization, we know that the amplitudes of both the X and Y component must be equal. So if that is the case, then 2XAY is the same as AX squared plus AY squared. So it means that, which is the overall light intensity. So it means that all of the light intensity is composed then within the 45-degree polarization. Similarly, for S3, we've got the degree of right-hand circular polarization. And that's defined as minus 2 times the imaginary part of EX EY conjugate, which works out as 2AXAY by sine of the phase difference between them. And again, we know for right-hand circular, or for any circular polarization, we know that the phase difference must be pi over 2 exactly. And again, sine of pi over 2 is 1. And similarly, for it to be circularly polarized and not elliptically polarized, we know that the amplitudes have to be the same. So again, the 2XAY works out as AX squared plus Y squared, AY squared is the same value. So essentially all of the light intensity then, in that case, is contained within the right-hand circular polarization. So if we have values for all of those Stokes parameters, then we can calculate, just using basic maths or simultaneous equations, we can calculate values for any of the component parts. And therefore we will know exactly what the state of polarization is. And also, given the significance of each parameter, once we kind of get familiar with it, by looking at the Stokes vector, we can tell very quickly what the state of polarization is. And those 4 parameters together make up the Stokes vector. So just have a look. I don't want to go through this in too much detail, but these are just some examples of Stokes vectors for perfectly polarized light. So we see, just for example, if we take the right-hand circular one towards the right-hand side there, we see that the S0 component is 1, which it is in all cases because these are all stated in a normalized way. There's a 0 S1, which means there's no linear polarization component whatsoever. No horizontal polarization component. Same for the 45-degree, and then a perfect 1 for the circular polarization. So if we had values in all of those Stokes parameters, just for example, instead of zeros, if we just had some sort of value in all of the parameters, what we'd be looking at then would be some sort of kind of hybrid. So we'd have elements of circular, linear, and 45-degree polarization. So you'd have some sort of elliptical polarization with an offset to the horizontal axis. Okay, so we have an idea of the different types of polarizations now and how the Stokes vectors describe those. So we'll look at how that's used in this method, Stokes vector direct detection. So the basic idea behind Stokes vector direct detection is that firstly, we transmit the modulated signal and the carrier on orthogonal polarizations. So on one polarization, we have the modulated signal being the combination of the information signal and the carrier signal. And then on the other orthogonal polarization, we've got just the pure carrier. And the idea of that is by keeping the pure carrier, we then have something to compare the received modulated signal to. So it's kind of a means of avoiding having a local oscillator, really. We then use an electrical circuit to detect the Stokes vector of the received signal. And then relying on step 1, we combine certain elements of the Stokes vector to reveal or to recover the original information signal. So that's the basic principle of this method. So this is kind of, this is the most common or one of the most simple circuits that we can use for that. So what we've got on the left-hand side coming in, we've got the combined signal. So that's the transmitted signal. That's coming into a polarization beam splitter. So that's splitting the signal between say the X and Y polarizations. Both of those are going into optical couplers. So that's just splitting each of those X and Y signals further. And then on the top and the bottom, we've got the X and Y going into what's stated as S1 here, which is a Balance photo detector. And then in the middle, we've got X and Y going into a 90-degree optical hybrid and coming out to 2 further balanced photodetectors. So I'll have a look at how that works in a second. First of all, if we look at S1, so the first Stokes parameter. So what's coming in at the top is X and what's coming in at the bottom is Y. Now we know that the balanced photodetector, it uses photodiodes, so it's a square law detector. So it's receiving, what it's actually receiving here is X by X conjugate, and then at the bottom we've got Y by Y conjugate. And then the output is the difference between the two. So X by X conjugate is the same as the intensity of X. Y by Y conjugate is the intensity of Y, and then the output is the difference between the two, which is what the first Stokes vector actually is. So straight away there, we've got the first Stokes vector. Then for S2 and S3, we need to rely on how the optical hybrid works. So we'll have a look at that first of all, just as an aside. So this is kind of a schematic of a 90-degree optical hybrid. It looks a bit intimidating there at the moment, but essentially what we've got coming through on the left-hand side is in port A and port B, we've essentially got the X and Y signals. Each of those couplers, we've got 4 couplers, A, B, C, and D. And each of those has a transfer function described in the slide there. So if we use that matrix in the slide, 1/√2, etc., and multiply that by the input 1 and input 2 into each of those couplers, we get the 2 outputs from that coupler. So essentially, if we start off with, in this diagram, it uses ES and EL, but in our case, we're talking about X and Y. And on the input to the first coupler, we've got X on the top and we've got 0 on the bottom. And then on this coupler B, we've got Y on the top and 0 on the bottom. And if we follow those through and multiply them each time by this transfer function, we get the outputs described in the slide here. So a half, in our case, X minus Y, or ES minus E low in this case. And then those feed into a photodetector. So if we let ES and E low be X and Y respectively, which is what we're talking about, then the 2 outputs of the balanced detectors here in this slide come to be the real part of X by Y conjugate and the imaginary part of X by Y conjugate. There's quite a bit of kind of complex multiplication and so on involved in that. I don't want to hog the slides with all of that, but I'm going to put those in the appendix at the bottom as to how that works out, just in case anybody's wondering about that. But essentially what we get out of those two, the important part is what we get out of those 2 balanced photodetectors is the real part of X by Y conjugate and the imaginary part. So if we go back to our electrical circuit here, we see then that S2 is the real part of X by Y conjugate and S3 is the imaginary part. Now, by simply summing S2 and S3, we've got the entire X by Y conjugates. We're summing the real and the imaginary part. So therefore we get X by Y conjugate. And if we remember that X is the modulated signal, which is essentially the information signal multiplied with the carrier. So that's essentially I by Y. And then Y conjugate is Y conjugate. So X by Y conjugate works out as I by Y conjugate. And Y by Y conjugate is just the intensity of Y being the carrier, which is a fixed constant in ideal terms. So what we get when we sum S2 plus S3 is simply a scaled version of the original information signal. So just by summing those two, we've recovered the information signal at that point. So that's kind of one of the most straightforward circuits that we can use for that. There's lots of different circuits that we can use. So this one here is just an alternate one. These were all taken, as the slides say, by the way, by a paper by the names mentioned there. So there's lots of different ways of combining it. This particular version uses an optical hybrid, and then instead of balanced photodetectors, just photodiodes. And it means that the outputs that we get from the photodiodes, they're not exactly what we're looking for. So we need to just multiply them by this kind of fairly straightforward transfer function. So just for example, here we've got S1 is going to be 1 times X squared plus 0 minus Y squared. So that's the first Stokes vector that we want. And then similarly for S2 and S3. So it's a slightly different circuit, but does the exact same thing really. One kind of complication with this method, it seems very straightforward so far, but one complication is due to the birefringence effect. I don't know why this reminded me of a marshmallow that I used to eat as a kid, but that's kind of the simplest way to understand it for me anyway. So if we can imagine that what we're transmitting is a perfectly orthogonal signal where we've got just the carrier on one polarization and we've got the modulated signal on the other polarization. But because of the birefringence effect, which causes the state of polarization to change as the signal moves through a waveguide, it means that what we receive on the far end is not going to be that perfect XY polarization and division between the carrier and the modulated signal. We're going to get some sort of a hybrid. So we need to work out what the rotation matrix is that caused that, or what we need to describe the rotation that occurred somehow. So a way of kind of describing that, I suppose, if we say that the transmitted Stokes vector is equal to the inverse rotation matrix multiplied by the received Stokes vector. So obviously what we detect using the circuits above is the received Stokes vector. So we need some way of calculating the rotation matrix to get back to the transmitted Stokes vector. There's three kind of common ways of doing it. We've got training symbol, signal distribution, and a blind adaptive equalizer. And we'll have a quick look at what each of those are now. The training symbol is kind of the simplest, and it's really like calibrating a piece of equipment or something like that. So what we do is we transmit a kind of a unit or a basis Stokes vector 3 times. So we start off with 1, 0, 0. So if you imagine here where the question marks are, that's not the inverse rotation matrix, but the actual rotation matrix. So we multiply that by the transmitted signal, which can be described as 1, 0, 0 Stokes vector. And that's going to give us whatever that is, X, Y, Z. So because it's just a straightforward basis Stokes vector with only one perfect polarization, the received Stokes vector X, Y, Z must be the first column of the rotation matrix. Just mathematically, because we've got zeros in the other two positions there, it must equal the first column. So then we repeat that for the two other possible basis Stokes vectors, the 0, 1, 0 and the 0, 0, 1, and we're able to fill the rotation matrix then based on that. Then once we have that, we can calculate the inverse rotation matrix, and away we go. The second one, signal distribution, is quite interesting actually. So this, I don't know if everybody's familiar with the Poincare sphere. I hadn't come across it before, but I've just been learning about it recently. So the Poincare sphere is just a kind of a graphical way of depicting the state of polarization of a signal. So you've got a sphere, and any point on the sphere is one particular type of polarization. And if it's within the sphere, it's some sort of hybrid of polarizations. If it's at the equator, it's linearly polarized. If it's at the pole, it's circularly polarized. And if it's anywhere in between, then it's some sort of combination, so some sort of elliptical polarization. So let's say if we're using, just for argument's sake, a 4-QAM modulation format, then the 4 points shown in the slide there, the 4 red dots, represent the Stokes vectors, or the states of polarization, for each of the 4 QAM positions that you can send, if you like, the 4 positions on the constellation diagram. So if we can imagine, if we transmit, what we're transmitting is what's shown in the diagram there. So it's like, you know, before any noise has come in or before any rotation has occurred, it's this perfect states of polarization. So we plot the 4 points on the Poincare sphere. We can then plot a plane that those 4 points make up. And then if we were to do the same for what we actually receive, for the Stokes vectors that we receive, having transmitted those 4 points, we'll find that what we receive due to the rotation is going to be a plane with a different orientation. And then using linear algebra, if we calculate the matrix necessary to rotate the received plane, if you like, back to the perfect transmitted plane, then essentially we've got the rotation matrix. We might have to, there's obviously going to be noise effects as well. So the received points mightn't actually form a perfect plane. They might not be in plane. But in that situation, we need to form a kind of or calculate a least squares plane. So similarly to how we'd fit a least squares line to a graph or something, we can calculate a least squares plane and then essentially use that. And then the third method is a blind adaptive, it's called a blind adaptive method. This, in summary, this basically involves transmitting something, seeing how far out we were with our rotation matrix, correcting it, and then repeating and iteratively improving it each time. So what we've got coming in here on the left-hand side is the 3 Stokes vectors, if you like. So this is 3 Stokes vectors related to the received signal. Each of the C1 and C2 and C3, those are complex coefficients. Now the S1, S2, and S3, they're real valued numbers. They're just scalars, if you like. So when we multiply those, we're essentially dot producting the Stokes vector with a vector of complex coefficients. So when we do that, we end up with one complex number, which represents a point on the complex plane. And then if we kind of say, okay, we need to know, of course, what modulation format we're using, but say we're using 4QAM again, where we've just got one point in each of the 4 quadrants of the constellation diagram. We transmit our signal, multiply it by our complex coefficients, and then we plot the resulting point on our complex plane. And we basically assume that it should have been the 4QAM point on the constellation diagram nearest to where that is received. So what we do then is we correct or we amend the complex coefficients to what they ought to have been in order to kind of have landed ourselves exactly on the point in the quadrant nearest to it. So if, for example, we transmit a point and we transmit a signal and the resulting point is in the first quadrant, then we know it should have been we assume it should have been the 4QAM point in the first quadrant. We amend our complex coefficients to get it exactly to that point, and then we go again, and we can amend it constantly. Normally, when using this technique, you would start off, in order to get your complex coefficients in the first place, you would start off with something like the training symbol or something like that, or some other method to get you started. This is a particular experiment that was described in the paper that most of this presentation was based upon. So this is where the guys who wrote the paper set up a particular circuit, transmitted and then recorded the signal using the Stokes vector direct detection method. So on the right hand side there, we've got some of the data in terms of they use 64QAM modulation format, bandwidth, and so on. But basically the circuit involves, so that they have an external cavity laser. The signal from that goes through a coupler, so that's split. And the idea of that is on the bottom kind of rung here, we've got the pure carrier here. And then on the top, we've got the carrier, and that then gets modulated with the information signal. The two of them then come into the polarization beam combiner, so they're both combined into the one signal on orthogonal polarizations, transmitted down the fiber cable over 160 kilometers. And then it's fed into a circuit which is not identical to the ones we've looked at above, but it's very, very similar. So they involve kind of a combination of the balance detectors and the individual photodiodes. So in order to get to Stokes vectors, they used a slightly different transfer matrix, but it's essentially the exact same principle. And an interesting thing about their findings is what they got was that we show that this is the frequency spectrum of the received data both before and after the rotation compensation, if you like. So the blue part here is before compensation for rotation and the red is after. And what happened is that before compensation for the rotation, the received X and Y values would have been kind of mixed, if you like. So both would have contained elements of both modulated signal and carrier. So instead of just a pure modulated signal on one polarization and carrier on the other, we've got both X and Y are going to contain combinations of both. And because of second order nonlinearities, so basically where you have a sine squared term or a cosine squared term, you're going to then have, because of the trigonomic identities of what sine squared is, you're going to then have frequency components of twice the original bandwidth. So we actually see that the width, if we leave out on the very extreme left and extreme rights, we've just got what is presumably noise. And then between about minus 13 gigahertz to plus 13 gigahertz, we've got the pre-rotation spectrum, which is exactly twice or approximately twice what the spectrum is after the rotation correction, if you like, which is from about minus 7 to plus 7 gigahertz. So it's about 13 gigahertz wide, and it's twice that before the rotation because of the combination or the mix of the X and Y components. This is just a kind of a comparison then of bit error rates between some different methods. So the green one on the left-hand side, that's polarization multiplexed coherent detection. So that's the coherent detection method we talked about above, and using polarization multiplexing, so we're sending information on both the X and Y polarizations. And then in the blue, we've got the Stokes vector direct detection. Then on the right in the olive color, we've got block phase switching, which is another type of direct detection, which I don't know a lot about, I have to admit. But we see that we see the point of this really is to see that in terms of the signal to noise ratio required for a given bit error rate, we see that the Stokes vector direct detection lags the coherent detection systems by about 6 decibels, but it's significantly ahead of kind of what represents some of the best of the other direct detection systems. And then a comparison of systems then. So we've got, in terms of cost, so direct detection, the IMDD is low in terms of cost and complexity. The polarization multiplex coherent detection is high in both of those elements, and the Stokes vector direct detection is low. So it kind of has the advantages of the intensity modulated direct detection systems, but also some of the advantages in terms of spectral efficiency, range, and bit rate, and so on, that the coherent detection systems have. So it's like a halfway house. It's got a lot of the advantages of one without disadvantages of the other. And that is the end of the presentation.